Hi everyone, we're starting lesson 16 or video 16, and we're going to be looking at dilations today. Okay, so dilations are basically when we talk about stretching graphs. Now graphs can be stretched either vertically or they can be stretched horizontally. The vertical stretch is easy. It's much easier than the horizontal stretch. Now let's start by actually doing a physical vertical stretch on a graph. So we're going to graphically show a vertical stretch. So let's assume that we start with the graph in the middle here that is in black, which we don't know what it's called, but we're just going to call it f of x. And the points that f of x are 0, 0, 3, 3, and 6, 0. Now, if I wanted to dilate it or stretch it vertically by 2 units, what that would mean is that we are going to take all of our y values and multiply them by the stretch or dilation factor of 2. In this case, the stretch or dilation factor is 2 because I want to stretch it 2 units. So that means that all the y values would get multiplied by 2. So therefore, my y value of 0, 0 means that I would go to 0 times 2, which is 0. So my point would stay at 0, 0. My point 6, 0 would go to 6, and it would stay again as 6, 0 because the y value 0 times 2 gives me 0. And my point 3, 3, I would take the y value of that 3, which is 3, and multiply that by 2. So it would go to 3 and 6. So the only point that would actually get stretched here vertically would be the middle point 3, 3, which would go to 3, 6. And then I would connect the lines together so that you can actually see a physical stretch of the y values. So when we're looking at vertical dilations, we're looking at stretching vertically or changing the y values so that the x values are not affected. The only values that are affected are the y values. Now, if my stretch is a number greater than 1, then I know that I'm going to have an actual vertical stretch. If my number that I'm stretching by is going to be between 0 and 1, then my image figure is going to be a reduction, meaning that it's not going to be a stretch, but it's going to be a shrink. So let's take a look at, for example, if I took the green graph now that I have here, which I'm going to call 1/2 f of x. So 1/2 f of x means that I am taking all my y values, okay, and with that I am going to be halving all of the y values. So I'm taking the original f of x graph, my original graph, and all the y values get multiplied by 1/2. So that, again, 0 times 1/2 will just leave me at 0 here. 0 with the 6, 0, the 0 multiplied by 1/2 will again leave me at the point 6, 0. But if I take 3, 3 again as my point of reference in the black graph that I want to reduce or I want to dilate, depending whether it's a stretch or a shrink, if I take 3, 3 and I multiply that by 1/2, that means that the y value, 3, multiplied by 1/2 will give me 3 over 2, and 3 over 2 is nothing more than 1.5. So here, my point would be 3 and 1.5. Okay, so I would just put those together, and you would see that it's not a vertical stretch, but it's actually shrinking vertically, and it's becoming shorter and stubbier. Okay, if we take a look at basically what this means then, is that we have anything that involves a vertical dilation means that I will take, as you can see in the box in here, x and ay, meaning that I'm multiplying my y values by some stretch or dilation factor a. So it would go from xy would go to x and ay. Or another way of looking at it, remember that we have x and f of x. That's like saying x and y. So I would be multiplying my y value, or my f of x, by a. Okay. Now, if I had to do this, let's try a new one. Let's try a different one, so that I have to find. I'm going to get a graph here. I'm going to use the graph y equals x squared. Okay, so the y equals x squared, I'm going to get 0, 0, 1, 1, 1, negative 1 and 1, and then 2 and 4, and then negative 2 and 4. So here's my original y equals x squared graph. And the way I got that was just by choosing some numbers. So I said x and f of x, or y. So I picked negative 2, negative 1, 0, 1, 2 for my x values. And my y values then, because it's equal to x squared, it would go to negative 2 squared would be 4, negative 1 squared would be 1, 0 squared would be 0, 1 squared is 1, and 2 squared is 4. And there are my points. So it's 0, 0, 1, 1, 2, 4, and then negative 2, 4, negative 1, 1, and there's again 0, 0. All right, let's put our parentheses around there. All right, now if I want to do, if I want to take the f of x graph, which I called x squared, okay, so my f of x graph is equal to x squared. If I want to take that graph and I want to have it undergo a vertical dilation of 1/2, that means that all of the y values are going to be halved. So therefore, half of 0 is just going to be 0, because 0 times 1/2 is 0. So my first point here in the middle, in the origin, 0, 0, stays where it is. I then move on and I say, well, the point 1, 1 will go to 1 times 1/2, which goes to 1 and 1/2 over here. The same thing will occur on the left-hand side symmetrically. And then the next one, 2 and 4, would end up going to 2, and 4 times 1/2 would go to 2. So it goes to 2 and 2, and then 2 and negative 2. So that my graph would stretch vertically. Or in this case, it's not a real stretch, but it would be a shrinkage. Okay. Now, algebraically, when we are looking at, so we've looked at how to do this how to do these problems graphically. How do I physically change my graph? I stretch it vertically by multiplying by whatever the value of the dilation factor is. So if the dilation factor vertically is 2, then I multiply my y values by 2. If my stretch factor is 1/2, I will multiply my y values by 1/2. Now, if I'm going to do this algebraically, so I want to know what the name of my new equation is going to be, I'm going to go through this process. So it says, find the image equation under a vertical dilation of 3. All right. So what that means is that because it's f of x means y, and it's my y values that are changing, because all my y values are being multiplied by the dilation factor, then I will isolate for y. In this case, in the problem I have, it's already isolated for, but the entire equation will get multiplied by 3, the dilation factor of 3. So the entire equation gets multiplied by whatever the value of a is, so that f of x will go to a of f of x, so that you will put the dilation factor in front of the entire equation, and the whole equation will get multiplied by 3. So that if I have f of x equals 2x plus 3, it will be 3 times 2x plus 3, which then, when I distribute, will go to 6x plus 9. Now, if I have to find the image equation under a vertical dilation of 1/4, well, given that f of x is equal to 2x squared plus 4x minus 8, so this is the problem that I have placed there for you, then what I'm going to do is, it's a dilation of 1/4. So I already know that a dilation of 1/4 means that I'm not getting really a stretch, but I'll be getting a shrinkage, okay? So that all I will do is I will take 1/4, and the entire equation will be placed inside brackets, and everything inside those brackets will get multiplied, will become multiplied by 1/4, so that I will get 2/4 x squared plus 4 over 4x minus 8 over 4, which, when I simplify, will go to 1/2 x squared plus 1x, or just x, and minus 8 divided by 4, which is 2. That is my image equation with a vertical dilation of 1/4. Okay, now the next thing we're going to take a look at is we're going to take a look at the horizontal dilations. Now the horizontal dilations are a little bit trickier. Just like when we had the horizontal movement of the graph that went in the opposite direction, so therefore if it said that you were moving to the right, then it would be x minus 3. If we were moving to the left, it was x plus 3. With the horizontal translations. With the dilations, we have a similar thing occurring. Now, let's take a very quick example. Take a look at an example where I am given the graph f of x. So my f of x graph is the black graph. So the black graph, okay, gives me the points 13, 1, 10, 3, 7, 1, 4, 3, and 1, 1. All right. If I want to find the image of the graph with a dilation factor of 1/2, because it's the x values, we're looking at a horizontal dilation, it means that it's the x values that get affected. If it's the x values that get affected, that means that I will take my dilation factor of 1/2, whatever it is, for the graph, okay, so for the graph, and I will take that dilation factor of 1/2 and I will multiply all of the x values by 1/2. So that starting at 13, 1, 13 times 1/2 will take my first point to 6.5 and 1. So 13 will go to 6.5. The point 10 will be halved as well, so it'll go to 5. The point 7, when it's halved, will go to 3.5, and the point 4 will go to 2. And then finally, my point 1, 1, my initial point here in the black graph of f of x, will go to 1/2 and 1. So that I have, as you can see, I have compressed my graph, so that when I have a value of that's between 0 and 1 for my dilation factor horizontally, if my value is between 0 and 1, my graph is going to get squished or compressed like an accordion. And if my graph is going to be larger than 1, my graph would stretch horizontally and it would open up. Okay. Now, once we've done that, let's do another example just very quickly. So if I had to find the image, for example, of 3 and -4 with a horizontal dilation of factor 3/2, because it is the x value that is affected, that means that I would take my x value 3 in the coordinates 3, -4. So I would take my x value 3 and I would multiply that by 3/2, so that I know that 9 over 2 is going to be my new value, or it would be 9 over 2 and -4. Now 9 over 2 is the same thing as saying 4.5. So it would go to 1, 2, 3, 4.5, and then 1, 2, 3, 4. So it would be 4.5, 9 over 2, and -4. Okay. Now, if I want to find the image of -2 and 1 with a horizontal dilation of factor 1/2, again, it's my x value, so the point -2 and 1 with a horizontal dilation means that my x value is affected, so I will multiply my x values by whatever the factor is to get the actual point or on the graph. So it would go to -2 times 1/2, which equals -1. Therefore, my new point would be at -1 and 1. Now, essentially what we want to do when we dilate or stretch a graph horizontally is that we know that the x values are the ones that change. The x values are multiplied by the dilation or stretch factor A. Now again, this is if I am doing it physically on the graph. I will take my x values and multiply them by the A units or stretch factor. So if I have, for example, I'll just give you a quick example here of I've got a point 2 and 5, and I'm doing a horizontal stretch, and I do a horizontal stretch of 4. That means that my x values will get multiplied by 4, and therefore it would go to 8 and 5. If I had, again, 2 and 5 as a coordinate, and I had to do a horizontal stretch of 1/4, then that would mean that I would do 2 times 1/4, which would take me to 1/2 and 5. So I would multiply exactly by whatever the vertical dilation factor is. I would multiply my x values by my values of by the values of the x. All right. On the other hand, though, when we have to do this algebraically, it becomes a little bit more complicated. With the algebraic method, what we need to do is not multiply by the factor of 4 or by the factor of 1/2 and so forth, but what we do is we multiply by the reciprocal of it. So, giving you an example, if I have y equals 2x squared under a horizontal dilation that has a factor of 4, what I would be doing is I would be saying, well, y has to equal 2 times 1/4 x, 1/4 of x, all squared. So that wherever there's an x, I would replace it with 1/4 x, or x over 4, for that matter. Okay, so I'm multiplying by the reciprocal. So the number was 4, so I multiplied it by 1/4. Okay, so that I would end up getting 2 times 1 over 16 x squared, which takes me to 1/8 x squared. Therefore, my new equation with a horizontal dilation factor of 4 would be 1 over 8 x squared. Now, the alternative way of looking at this would be to do this form that we used also for the translations, so that I would say my alternative way of doing this would be, or it would be my new value of x, x prime, has to equal 4 times my old value of x. Okay? But because I want to isolate for the old value, then I would say x prime over 4 is equal to x. And because we don't want to have to deal with x prime anymore, then we would say that wherever there's an x, we would just replace it with x over 4. And that's exactly what I did over on the left-hand side. So just to show it, I would say y is equal to 2 times, well, wherever there's an x, I am replacing it with x over 4. So it's 2 times x over 4 all squared, which still gives me x squared over 8, or 1/8 x squared. Means exactly the same thing. Or 1/8 x squared. All right, so if we had, for example, the image of -2, 1 under a horizontal dilation. So here, let's go back, and we've got a point. So we've got a single point, not an equation, but we've got a single point, and it has a horizontal dilation with factor 1/2. That means that I would just take -2 and multiply that by 1/2, and that would give me -1. Therefore, the point would be at -1 and 1. So here, again, if it's going right on the graph and you're looking at a single point, then the single point, you would take whatever your factor is, which is 1/2 in this case, and multiply the x value by that 1/2. If, on the other hand, we are looking at a situation where I am looking for the value of the new equation. So if I have f of x equals 3x squared plus 4x minus 5, and I've got a horizontal dilation with a factor 1/2, that means that wherever I have an x, I will replace it with 2x. So how did I come up with that? Because I took the reciprocal. I took the reciprocal of 1/2, and the 1/2 is going to go to 2. So wherever there's an x, I would replace it with 2x. So that I end up getting f of x is equal to 3 times 2x all squared plus 4 times 2x minus 5. And then I would just simplify that, so that this would go to 3 times 4x squared plus 8x minus 5. And the final answer would be 12x squared plus 8x minus 5. All right, so again, if we wanted to do this the longer, more convoluted or more complicated manner, then I would say, let my new value of x, x prime, equal 2 times, or equal 1/2. Let it equal 1/2 my old value of x. Now, because I want to isolate for my old value of x, then this would go to 2x prime equals x. So now, wherever there is an x, I will replace it with 2x, which is exactly what I did above here. Okay? So again, I would just end up with f of x is equal to 3 times 2x all squared plus 4 times 2x, and then minus 5. Okay. Now, let's do a couple of other examples here, because I think it's important that, that we get the gist of this. So it says, find the image equation of y equals 2 over x under a horizontal dilation with factor 2. So that means that wherever I have an x, I will replace it with x over 2. So that I'll say y is equal to 2 over x over 2. And therefore, that ends up giving me y is equal to 2 over 1 divided by x over 2, which will give me y is equal to 2 times 2 over x, which becomes 4 over x. So y equals 4 over x. Okay. The last thing I want to just very quickly take a look at are the dilations that have a center at the origin. So you have with a center at the origin. So one of these, you're going to have your point of reference being at the origin. So when we have dilations with center the origin, both x and y coordinates are going to be multiplied by the dilation factor a. So for example, f of x is the black function. Again, here, we're going to do this again physically on the graph first. So f of x is the black function, and if you dilate it with the center at the origin, and the dilation factor is equal to 2, then that means that x and y will both get multiplied, so that I will have ax and ay. So my points 1, 2, 4, 3, and 3 and 5 will each consecutively go to 2, 4, 8, 6, and 6, 10. I multiplied both x and y by 2, both x and y by 2, and both xy by 2. So if my value of the a is larger than 1, then I know I have an enlargement. And if my value of the a is going to be between the numbers 0 and 1, or it'll be a fraction, then I know that it's going to be a reduction. Or the graph is going to get smaller. It's going to reduce in size. All right. So algebraically, though, if we want to do this, we're going to do, again, the opposite as we did with the horizontal, dilation. So that if it says that to find the equation, so we want to find the equation of y equals x squared. So we're going to do this from scratch. If I want to find the equation of, what the new equation is of y equals x squared, that's been dilated with a center 0, and it has a factor of 3, what that means is that wherever I have an x, I will replace it with x over 3, and wherever I have a y, I will replace it with a y over 3. So that I will then say, since it's y is equal to x squared, I will say y over 3 is equal to x over 3 all squared, so that I have y over 3 is equal to x squared over 9. And then I will multiply here across the 3, so that I will get y is equal to 3 times x squared over 9. And then I will simplify here, so that I get y will equal x squared over 3. And that is my new equation of that line, or of that graph, given a dilation through the center 0, and that with a factor of 3. Okay, that's it. I will see you next time.